remember here, x is essentially just a constant with respect to the Laplace transform. Okay, so my apologies with that being repeated. So, the Laplace transform of cos of at is equal to s squared over s squared plus a squared. So therefore, the Laplace transform of cos of tx, so in this case, a is equal to x, is just equal to which is x, over s squared plus a squared, which is x squared. So now we know that this term is going to be replaced with this term. And that's what we have on the next slide. So that's the Laplace transform of L of t semicolon p, which is equal to the integral from 0 to infinity of this times by the Laplace transform is equal to this the integral of this component, which we had before, times by the Laplace transform, which we resolved here, and then if I just put it together, just cleaning it up a little bit, is the integral from 0 to infinity of s over x squared plus p times by s squared plus x squared dx. So now the next step is just really simple. I've just applied a partial fraction decomposition. If people would like to see that in more detail, I'm assuming that if you're doing integrals of this nature that you probably are very well aware of partial fraction decomposition. If you're not, however, and absolutely no worries if you're not, please let me know in the comments or send me a direct message, and then I will add an extra component to this video where I explain the steps. But basically, with partial fraction decomposition, we're able to take this combined fraction, so like these two fractions multiplied by each other, and we're able to separate them out. And the beauty of that is it then makes it very, very easy to integrate. And so the partial fraction decomposition of this term is s over s squared minus p, 1 over x squared plus p minus 1 over s squared plus x squared. So again here, these individual components are very, very easy to integrate. But put together like this, it would be a very, very nasty method. As I said, that's why, I've said this in a number of videos, but it can be very difficult to know exactly what step to use and where. I personally have no actual written methodologies associated with, here's an integrand, here's how I solve it. Do this, do this, do this, do this. No, it is just practice and picking up on patterns. So when I see this, I've looked at these things before, I go, oh, boom. This individual component is very easy to integrate. This individual component is very easy to integrate. Let's see if I can apply a partial fraction decomposition to separate them, and therefore I can then just take it from being a term I can't integrate into two terms I can integrate. Okay, so here s and p are obviously, these are just constants with respect to the integral, which is with respect to x, my apologies. So that's why we've drawn it out the front. And then just integrating each term, 1 on x squared plus p, plus p, is just 1 over the square root of p, arctan of x over the square root of p. Similarly for arctan, 1 over s squared plus x squared, this is just 1 over s, arctan of x over s. Now if you wanted to do these individually, or once again, if you would like to see a video showing this, all I've done in this case is let x equal the square root of p times by tan theta. And then in this situation here, I've let x equal s tan theta in order to integrate it. And it's a very, very simple integral with just some basic trig identities. Okay, now remember that p is a positive value, and obviously when we take the square root, it can be a positive or a negative value. Because we are just dealing with positive values in this case, we're going to only be dealing with the positive solution. And in fact, actually, this is not 100% technically correct. It should really be over the absolute value, and that comes about once again from doing the substitution that I mentioned before. S, we had s squared, so obviously taking the square root s, well, can it be positive or negative? Remember that when it comes to s in the Laplace transform, it is technically a complex number, and its real component is, the magnitude of its real component is greater than 1. So s is a positive value in this situation. So we know this is positive, and we know this is positive, and that's important because when we apply the limits, it can either be negative infinity or positive infinity, and they give different values. So arctan of infinity, remember here for both, we've got infinity divided by something. Because it's infinity divided by a non-zero positive value, it just remains itself as being infinity. So we have arctan of infinity here, arctan of infinity, which is just equal to pi over 2, which is what we've got on this line here. So we've got 1 over the square root of p times by pi over 2 minus 1 over s, arctan of infinity again, which is pi over 2. Arctan of 0 is just equal to 0, and so therefore we have minus 0 and 0. So this is the upper bound substituted in, and this is the lower bounds. This completely disappears. What I've done in the next step too is I've just dragged out the pi over 2, and so we're left with 1 over the square root of p minus 1 over s. So the next step here is just to put it all over a common denominator. So firstly, I've done multiple steps in one, so I'll just explain each individually. Firstly, the pi over 2, let me just get rid of that. The pi over 2 here is just what we have here. in terms of what we have here, I'm just putting it over a common denominator. So s minus the square root of p over s times the square root of p, which is what we have here. Now s over s squared minus p, remember p is a positive value, so we can just complete the square, and we have s plus the square root of p times by s minus the square root of p. And so that's why we've got these terms here. We can see here that we can simplify quite a bit. So this component here cancels out with this component here. This s cancels out with this s. And so what we're left with is pi over 2 times by the square root of p times by s plus the square root of p. So again, taking it from a much more complicated expression, which we have here, down to a very simple expression. So this is the Laplace transform of the integral. Because we want L of t semicolon p, we now take the inverse Laplace transform, which is the next step. So L of t comma p is equal to the inverse Laplace transform of this term. Remember, it's just with respect to s, moving it back to t. So this component and this component is just a constant, so we can bring it out the front. The inverse Laplace transform of 1 over s plus square root of p, which is just equal to e to the minus square root pt. So if you're unsure, just look up in your Laplace transform tables. 1 over s plus a becomes e to the negative at. Very easy to prove that as well. Again, if people would like to see a video showing that, comment or send me a message and I'll be happy to put that together. Okay, so now we've got our L of t semicolon p, which is obviously a much more complicated form than the integral that we're actually looking for. So, you know, I mean, we're looking to just deal with this expression here, but we could actually very easily extend this to have the t as well. Nevertheless, we are just dealing with this, so we now need to get k of p, and the way that we get that is by evaluating L of t semicolon p at t is equal to 1, which is what we have in this step here. So k of p, which equals L of 1 semicolon p, is equal to pi over 2 square root p, so it's just this value evaluated at t is equal to 1, e to the negative root p, so obviously that multiplied by 1 is just itself. And so therefore, Jn of p, which is what we want to find here, which is equal to negative 1 to the n over n factorial times by the nth derivative with respect to p of k of p, which is what we have here, is equal to negative 1 to the power of n, over n factorial times by the nth derivative with respect to p of k of p, which is what we have here, just pi over 2 pi over 2 square root p times by e to the negative square root p, which is what we have here. I've just made it just a little bit simpler by dragging out the constants. Obviously, pi is a constant, 2 is a constant, so I've just brought that out the front. The pi goes there, the 2 goes there, and we just have the resultant expression. And so therefore, our integral that we wanted to solve, Jn of p, which equals the integral from 0 to infinity of cos of x over x squared plus p is a positive value, to the power of n plus 1, where n is a positive integer greater than or equal to 0, is equal to negative 1 to the n times by pi over 2 times by n factorial, and then it is the nth derivative with respect to p of e to the negative square root p over the square root of p. Now, I imagine for some people that may be watching this, that's a very unsatisfactory solution, because I've essentially just taken an integral and converted it into a derivative. So this isn't really, for me at least, it's not a closed form solution. You know, a closed form solution would have an absolute expression or some sort of formula associated with it. Here we're just basically saying you get this, and then if you want to, if you want to evaluate it for 2, you take the derivative twice. If you want to have it to the power of 4, you take the third derivative, and so on and so on. So if someone knows, and I was just playing around with this on the bus on the way home, so I didn't go into any further detail, but if someone can actually take this from being a derivative term, which is what it is now, and convert it into some sort of sum of a to the n times by something, where a of n can be resolved into some sort of magical expression, n factorial over e to the power of n plus 2, whatever. That would be absolutely amazing, but at this stage, I think it's pretty nice on its own. So if we were to have a look at some values, for instance, I've just got Wolfram alpha here, so let's just deal with the first one. So d on dp, of e to the power of square root of p divided by the square root of p. So this would be the case where we have it to the power of 2 on the denominator. And we see that we have this expression here. Say we wanted to do it so going back to here, let's say if we had 3 on the denominator here, which would be n is equal to 2, so we're taking the second derivative. Oh, notice how I haven't multiplied by this term either, so just remember we haven't included that. So if we took the second derivative, where am I? Power of 2 over d to the power of 2. We have this, and maybe just one more. Let's go to the third derivative and see what it looks like. So you can see here, looking at different values, there's obviously a couple of common things that come about. We obviously have p to the power of, that looks to be 2p plus 1, 2n plus 1 divided by 2. We have e to the square root p, which seems to be common. But if someone knows how to find an expression to generate this component within it, please comment and let me know, because that would be fantastic. Anyway, coming back to it, obviously that's the end of the video. I hope you've enjoyed it. If you have, if you could please like the video. If you would like to see more videos like this, please hit subscribe. And as I say in all of my videos, if you have any suggestions or requests of things that you would like to go over, please either comment here or send me a direct message. And